Okay, welcome to the revision class for the second exam. Okay, uh, so one of the topics that we dealt with for this second exam is the random variables. Which, if we are in a probability triple omega f p, it's a function x that is going from the sample space omega onto R. Okay, in such a way that the pre-image of the sets minus infinity a are in F for every a in R. Okay, so these are equals to all the omegas such that x of omega is less or equal less. Let's put less or equal than a. Okay, there is two types of random variables. Oh, there is more than two types, but there is two types that we study, which are discrete discrete random variables, which are such that the image of x, which we are writing it as, by definition, all the x in R, such that the probability that x is equal to x is positive, this is a discrete set. Okay, and so to be able to make sense of this, we need that there exists a countable set S contained in R such that the probability that x is in S is equal to 1. Okay, so this is a discrete random variable. Okay, so in this case, what we can do is these random variables are completely defined by the value of the probability in each point of the image. Okay. On the other hand, we can also look at continuous random variables. So we're going to look at continuous random variables if there exists a function f, let's say of x, that is going from R to R plus, such that the probability that x is less or equal than a is equal to the integral from minus infinity to a of f of x dx for every a in R. Okay, and so the main difference is that the probability that x is equal to x is equal to 0 for every x in R if x is continuous. Okay? So the point is that discrete random variables can give mass or probability to specific points, but continuous random variables don't give mass to specific points, but give mass to open sets. Okay? Continuous random variables have positive probability of being in certain intervals. Okay? And in particular, the probability that A is less or equal than X, less or equal than B. And so here this is also equal to the probability that A is less than X, less than B. This is equal to the integral between A and B of f of x at x dx. Okay, so we can actually integrate, and this is like this is what's called the density function of x. Okay, so what is a main concept between random variables? So independence. So we say that x, y random variables are independent if the probability that x is less or equal than a intersection y is less or equal than a is exactly equal to the probability that x is less or equal than a times the probability that y is less or equal than a. Okay? For discrete random variables, this is equivalent, and here there would be x is less or equal than a, y is less or equal than b is equal to the probability that x is less or equal than a times the probability that y is less or equal than b. Okay, and this is true for any pair of product spaces. So the way that for discrete random variables, we can actually say that the probability that x is equal to a intersection the probability that y is equal to b is exactly equal to the probability of x is equal to a times the probability that y is equal to b. Okay, but this is only for discrete random variables. Okay, this is also equivalent, independence, for continuous random variables is also equivalent to the density function of the joint distribution f of xy at xy is equal to f of x at x times f of y at y, where f of xy is the joint density function of x and y. So in particular, what does this mean? This means that the probability that x comma y as a vector is in a set C is equal to the integral, the double integral over C of f(xy) in x evaluated xy dx dy. Okay, so the integral of this is over C. Okay, so random variables are independent if their joint density function decomposes into the product of the density functions. Okay, so if you are told in an exercise that they are independent, then you can actually just sort of assume that the joint density function is given by this product. What else? Also, if x comma y are independent random variables, then g of x and h of y are also independent, are also independent for any continuous functions g and h. Okay, so the point is that if you have random variables and then you apply some continuous linear function, continuous function to it, which can be whatever you want, depending on the application, they can be different things. If you know that they are originally independent, then whenever you take any function on top of them, they will still be independent. What else? Also, the expectation if x and y are independent, then the expectation of x times y is equal to the expectation of x times the expectation of y. So as a corollary, we can actually show that the variance of x plus y, so if x and y are independent, then the variance of x plus y is equal to the variance of x plus the variance of y. Okay, and the main point is this. Okay, and usually what we call when two variables are this, which are not necessarily independent. Okay, so this implication is not true. If you have this property, it doesn't mean that your random variables are independent. These things are usually called, they are decorrelated. Okay, we talk about correlation, but we are actually going to have something on correlations in the exam. Okay, so I guess now, so one of the things I said before is that for joint random variables, for jointly continuous random variables, x comma y, we can actually we can calculate the probability that x comma y is in a particular set C. Okay? And this is just given by the double integral over C of f of xy evaluated at xy dx dy. So let's look at an example. So let's say that x comma y are independent and identically distributed. Okay, so independent, and this is identically distributed. And with distribution uniform in the -1, 1. Okay, so then what we would have is that the joint mass function of f of xy at x and y is going to be equal to f of x at x times f of y at y, and this is going to be equal to, okay, so the density function for x is equal to 1/2 times the indicator of -1, 1, and this is also 1/2 times the indicator of -1, 1, which this just means that this is equal to 1/4 if x comma y is in -1, 1 squared and 0 otherwise. Okay, so sort of the picture that you can have in your head if this is x and this is y, the values that they can take, x comma y is uniform on the square with side length 1. Okay, so any point the pair xy takes, the pair xy lands in this square with equal probability, well, like equal probability for every point. So in particular, let's say, for example, if we want to calculate the probability it lands in the unit disk. Okay, so here the unit disk would be this thing here. What we need to do, we need to, okay, so the unit disk is equal to all the x comma y in R2 such that x squared plus y squared is less or equal than 1. So in particular, one of the things is that the unit disk is contained in the unit square. So in the definition, definition of the joint mass function, we only care about this value. But if we had a set that goes away from the unit square, we should know that the probability that you're there is going to be 0. So the only thing that we care is about the intersection between this set and the unit square. Okay, so then in particular, the probability that x comma y is in D is going to be equal to the double integral over the unit disk of f of xy dx dy, but this is just equal to the integral over the unit disk of 1/4 dx dy, which is just equal to the area of D over 4. Okay, so this is just pi over 4. Okay, so the probability, so let's say you're throwing a dart and you're good enough that you can actually know that you will land in any point in the unit square without really knowing where it can land. So the probability that you actually hit your target, which is the unit disk, is going to be pi over 4, okay? Which is a number which is fairly close to 1. And the point is, what are the what is missing is when you hit a point here which is not in the unit disk. Okay, but these are unlikely that will happen. Okay, and this is a fairly simple example. It could be a little bit more complicated, like some other relationship between x and y. Okay, something we had made quite a bit of emphasis on was the expectation of a random variable. Okay, and so the way that I think about expectation is the following. When you flip a coin, the expectation that is going to be a 1 or a 0 is 1/2. Okay, so it has like the same probability of being a 1 that being a 0. So what you expect that it will behave like is it's going to be behaving like the number 1/2. So the number of heads after n tosses would be n over 2. Okay, so that's intuitive. So the point is that for a random variable that is a bit more general than that, you can still start thinking of what would be the average behavior. Okay, so the expectation of a random variable is the average behavior. Okay, so for a discrete random variable, we're going to have that the expectation of x is going to be the sum of x in the image of x of the product of x times the probability that the random variable is equal to x. Okay, so that's for discrete. And for continuous, so for continuous, this definition doesn't work because clearly this is 0 for every x. So then this would be 0. But here we have to give a integral representation of this. For continuous random variables, the expectation of x is given by the integral from minus infinity to infinity of x times f of x dx. Okay. Okay, something we didn't quite look at much in class, but is something that can be useful, is the conditional expectation so for a given event A. Okay, so in the discrete case, the expectation of x given an event A is the expectation of x times the indicator of A over the probability of A. Okay, so I mean in general, so if we have discrete, so the point is, like, let's say that we know that the event A is happening, so how does this affect our information for a random variable? And the point is that now you need to think of, okay, what would be happening with the values of x if I condition on the value of on a happening. Okay, so for the discrete random variables, the expectation of x given a is equal to the sum of x in the image of x. So yeah, in x over the image of x, and this could also be intersection a of x times the probability that x is equal to x given a, okay, where this is just the probability of x equals to x intersection a over the probability of a. Okay, and for the continuous case, for the continuous case, I mean, we need to be a bit more careful, and the point is we actually need to look at what is happening with this random variable and how we can actually write it down. Okay, I'm not going to write it down because I guess we're not going to actually use it for the exam. Okay, so following similar to the law of total probability. So similar to the law of total probability, we have that if omega can be separated in the union from I equals to 1 up to infinity of AI, okay, and AI intersection AJ is equal to the empty set, then the expectation of x can be written as the sum from I equals to 1 up to infinity of the probability of AI of the expectation of x given AI. Okay, so this can be helpful in some of the exercises, especially in the Galton-Watson process. So you can actually take the expectation given the previous step being a particular value, and then sum over the probabilities of the previous step being the specific value. Okay. This is just following the definitions. Okay, so I guess I talked about variance before, but the next part that you should remember is the variance of a random variable. Which measures how far does a random variable differ from its average. Okay, so what is the variance of x? The variance of x is the expectation of the difference between x and its average. Expectation of x squared, which can actually be rewritten as the expectation of x squared minus the expectation of x squared. And this is always positive, and this is by Cauchy-Schwarz. Okay. So a typical thing that we're going to be looking at the mean and the variance for the central limit theorem. So example. So let xi I equals to 1 up to infinity, IID. Okay, so independent identically distributed with mean mu and variance sigma squared. We define Sn, which is the sum of xi, I equals to 1 up to n. Then what we can actually see is that for instance, the expectation of Sn is going to be equal to n times mu, and the variance of Sn is equal to the variance of x1 plus xn. But what we had said before, the variance of independent random variables is the sum of the variance, so this is just n times sigma squared. Okay. All right. So okay. So this is the think of random variables in general. So one of the things that we'll be looking at is the 3 types of convergence. So we're going to say that xn converges to x in distribution if fn of x converges to f of x for every continuity point for every x continuity point of f. Okay, so this is the distribution function from xn, and this f of x is the distribution function for x. Okay, so just a reminder, f(x) at x is just the probability that x is less or equal than x. Okay, and this is continuous in the case of continuous random variables, and it has jumps in the case of discrete random variables. Okay, so this is one type of convergence. Another type of convergence is that xn converges to x in probability if for every epsilon bigger than 0, the probability that xn minus x is bigger than epsilon goes to 0 when n goes to infinity. Okay, so that's another type of convergence. And then finally, the third type of convergence is we're going to say that xn converges to x almost surely if the probability of the set omega in omega such that xn of omega converges to x of omega is equal to 1. So this is equivalent to the probability of the supremum. If this is equivalent to, for every epsilon positive, the probability that the supremum of m bigger than n of xm minus x bigger than epsilon goes to 0 as n goes to infinity. Okay, and there is a clear relationship between these types of convergence, which is the following theorem. Almost sure convergence implies convergence in probability, which implies convergence in distribution. Okay, and the point is that you can go back on some of these. Okay, so remark. We can invert some of these implications under more conditions. For instance, for example, if the probability, so we know that if xn converges in probability to x, then for every epsilon, the probability that xn minus x is bigger than epsilon goes to 0 when n goes to infinity. If, moreover, the probability, the sum over n up to 0 or to infinity of the probability that xn minus x is bigger than epsilon is finite. Okay, so this is a bit stronger than convergence in probability. Then xn converges to x almost surely. Okay, and these are the type of implications we've seen in class. Okay, so but we can also see that that these implications are sharp in the sense that you can always find one sequence of random variables which will converge in distribution but not converge in probability and not converge almost surely. Then you can find another random sequence of random variables that converges in probability but does not converge almost surely. And we will, of course, then, I mean, you can like do these things particularly. Okay, so let's look at an example. So we take xn, which is uniform between 1 over n, 2 over n, and so far up to 1. So what does this mean? This is a discrete random variable. So this is a discrete random variable such that the probability that xn is equal to I over n is equal to 1 over n for every I in 1 through n. So what we can sort of see is that xn converges in distribution to x. Okay, so one of the things that convergence in distribution has is that this convergence is independent of the underlying probability space. Okay, so Xn can be defined in a different probability space than what X is defined on. Okay, so Xn, for instance, can be defined in omega n, which is equal to 1 over n 1, and X, so X here is going to be uniform in 0, 1, and X is defined, so this is for Xn, and omega, which is equal to 0, 1, is for X. Okay, so this is a continuous random variable and this is a discrete random variable. Okay, so in particular, so if we look at the probability so if we look at the probability that Xn is less than A, if we look at the probability that Xn is less or equal than A, this is going to be equal to, okay, so what is this going to be equal to? This is, so morally what you have to do, so let's say that we have 0 here, we have 1 here, so we have a point A, which is here in the middle. So then what you need to count is sort of A is going to be between I over n, okay, so there exists I such I in 1 through n such that I over n is less or equal than A, which is less than I plus 1 over n. There exists a unique I0 such that I0 is less or equal than A, that is less than I0 plus 1 over n. So then the probability that Xn is less or equal than A is going to be I0 over n. So one of the things that you can realize is, in particular, A minus I0 over n is going to be positive, and it's going to be less or equal less than 1 over n. But then if we look at the probability that X is less or equal than A, so X is now the uniform, it's uniform in 0, 1, so then the probability that X is less or equal than A is going to be equal to A. So then in particular, the probability that Xn is less or equal than A minus the probability that X is less or equal than A is just going to be differing by 1 over n. So the probability that Xn is less or equal than A minus the probability that X is less or equal than A in absolute value is going to be less than 1 over n for every A. For every A. Okay, so taking n to infinity, we can actually show that this guy is converging distribution. Okay, so what is a different example? So for convergence, almost sure, for convergence in probability, and almost sure convergence, we need the sequence xn, n in n, and x to be defined in the same probability space. Okay, so in particular, we can take xn, which is now defined in 0, 1, xn, which is now defined in the 0, 1, xn defined in omega equals to 0, 1 by the rule xn of omega is equal to, let's say, I omega over n, where I omega is the least upper bound for omega. So meaning that omega is less than I omega, is bigger than I omega minus 1 over n, which is less or equal than I omega over n. Okay, and this is for every omega. Okay, and similarly, x of omega is equal to omega for every omega in 0, 1. Okay, so in particular, if we look at the distance between x, okay, so similarly to what we have done for the distribution function, if we looked at the value of xn omega minus x omega, this is equal to, this is less or equal to, okay, so what we can realize is that x omega is equal to omega, and xn of omega is equal to I omega over n, where I omega over n is slightly bigger than omega, but it differs from omega by less than 1 over n, okay, similarly to the computations that we did over here. So then this thing here is less than 1 over n for every omega in the sample space, which is just 0, 1, which this implies that xn converges to x almost surely. So here what we have actually shown is that xn converges to x for every omega in the sample space. Okay. So, I mean, I think it's a good idea to look at this problem a little bit graphically. So if we have the sample space, which is given by 0, 1, and here in this axis we have x or xn, so x is given by this, and xn is going to be equal to, so let's say here 1 over n, so it's going to be equal to 1 over n, then it's going to have a jump, so at this point they coincide, which is 1 over n. At 1 over n is going to have a jump to 2 over n, here there is 2 over n, and then we have another jump, and another jump, and another jump, another jump. And the idea is that the distance between these two curves, the maximum distance between these two curves is given in any point here, and the distance here is 1 over n. Okay, so I think it's a good idea for you to think about this type of convergence maybe to think in the 0, 1 and try to think like some simple convergence to 0 or something like that. And now you can think of discrete random variables that work in a particular way. For instance, you could take indicators and see how they're working. Okay, so you could just take xn to be the indicator of an, which in this case what you are going to have is here the 0, 1, and now an is an interval here, and so if here we have 1, this is the graph of xn. So now you can start thinking of what happens when an starts moving around the interval to see what is happening. Okay, so you care about the size of an and also the position. Okay, we care for almost sure convergence. We care about the size of an and its position. For convergence in probability, we only care about the size. Okay, so that's a bit of the difference between convergence of probability and convergence in distribution. Okay, now for what I would say the last topic for this revision will be the branching process. Or Galton-Watson. Okay, so we take, so it depends on the notation, but yeah, so let x be a discrete random variable, with values in n star, which is equal to 0, 1, 2, 3, so on. Let x be a discrete random variable with values in n star, which is completely defined. By pk, which is equal to the probability of x is equal to k, where k is n star. Okay, so sometimes we'll give the values of pk to talk about this discrete random variable, and this is x is a discrete random variable, okay, and x is the distribution of the amount of children, let's say, children that an individual will have throughout its life. So morally, what I'm saying is like X is just sort of tailored to, let's say, your family, to like your contagion of the coronavirus or these kind of things, is like how many people are you going to make have the disease, or you're going to have how many children are you going to have. Okay, so we start So we consider Zn, which is the Galton-Watson process, Cn, n equals to 0 up to infinity. We consider Cn, n equals to 0 to infinity. A family of random variables, that a family of discrete, let's say, random variables that models the size of the population at the generation n. Okay, so Zn models the size of the population at the generation n, and so in particular what we have is Z0 is equal to 1, so we start with one infected person, or we start with one person, and then Z0, this one person will have offsprings, Z1, okay, which is distributed like X. Okay, and then C2, okay, so this is the first generation, and then here now you have X children, where X is a random thing, and so now you can start thinking, okay, how many children can this have? Well, it depends how many children you had at the beginning, and then you keep going, and then this process becomes zeta 2 and so on. Okay, so in particular, what we can write is that zeta n is equal to the sum of I equals to 1 up to zeta n minus 1 of xn minus 1 I, where xj I, this is just a family, over j and I are independent and identically distributed with distribution x. Okay, so everybody that is in each generation has the same probability of having k children. Okay, so in particular, so using the law of total probability for conditional expectation, we have that the expectation of zeta n is going to be equal to the sum of k bigger or equal than 0 up to infinity of the probability that zeta n minus 1 is equal to k times the expectation of zeta n given zeta n minus 1 is equal to k. Okay, so this is conditioning on the event. So here, let's call it ak is equal to the event that zeta n minus 1 is equal to k. Okay, and this is a partition of the sample space. So in particular, if we know the generation n minus 1 had size k, then zeta n is equal to the sum from k, so let's call it I equals to 1 up to k of x n minus 1 I. So in particular, the expectation, but these are all IID, so then in particular the expectation of zeta n given zeta n minus 1 is equal to k is equal to k times the expectation of the original discrete random variable x. So then the expectation of zeta n is equal to the sum k equals to 0 up to infinity of the probability that zeta n minus 1 is equal to k times the expectation of x. So in particular, this thing here is just so if this is a constant does not depend on k, and this sum over k is just the expectation of zeta n minus 1. So here we have a sort of recursive formula of how to calculate the expectation of zeta n. The expectation of zeta n is equal to the expectation of zeta n minus 1 times the expectation of x. So in particular, remembering that zeta 0 is equal to 1, this implies that zeta 1 is distributed like x, which implies that the expectation of zeta 1 is equal to the expectation of x. This implies that the expectation of zeta n is going to be equal to the expectation of x to the n. Okay, so morally we have two cases. So this is what we were calling R0. So if R0 is less than 1, then the expectation of zeta n goes to 0 when n goes to infinity, which implies that zeta n which implies that the population gets extinct. Okay, so if R0 is less than 1, we definitely know that the population gets extinct. But if R0 is bigger or equal than 1, we can still calculate the probability of extinction calculate the probability of extinction using the generating function. Okay, so here what we're going to have, and we're going to take the notation psi of s is equal to the expectation of s to the x. Okay, so this is the generating function for x. So what are the properties? So one of the properties is that if xi are IID, then the generating function of the sum at S is just going to be equal to the product of the generating functions. So morally what we're using is when we take an exponential of a sum, this is the product of the exponentials, And using independence, we can actually separate them all. So this is just going to be the product, phi x2 s phi xn s. And so this thing here is just phi of, let's say, the generating function x. So these are ID with distribution x. So this is phi x of s to the n. Okay, so that's one of the properties. The second property is that if we consider n a random variable, with values in the natural numbers, then if we consider n a random variable with values n and define t, which is equal to the sum from I equals to 1 up to, this is a random variable n of xi, then what we have is that the generating function of t at s is the generating function of n evaluated in the generating function of x at s. Okay, so this is the type of results that we need exactly from the branching process, because for the branching process what we have is we have the sum of independent identically distributed random variables, where the sum is up to a certain other random variable. So this used in the Galton-Watson process is telling you that phi of zeta n is going to be equal to v zeta n minus 1 applied to phi x of s, which in particular implies that this is just phi x, and this is the composition of phi x a lot of times s, n times at s. Okay, so the idea of these results put here is because for the Galton-Watson process they really make sense. So let's look at the proof just for you to have an idea of how to remember that we need these kind of things. So the proof is just if we take 1, the phi of the sum at s, this is just going to be the expectation of s of x1 plus xn. But what I was saying earlier is that the exponential of the sum is equal to the product of the exponentials. But now by independence, this is equal to the product of these exponentials. But this is, if this is equal to the products of the exponential, they are all identically distributed. So this is by identically distributed. This is the expectation of Sx to the n, which is just phi x of s to the n. Okay, for the second one, we do the same trick of law of total probability. So phi t of s is the expectation of s to the t, which is by law of total probability, this is the sum from k equals to 0 up to infinity of the probability that n is equal to k of the expectation of st given that n is equal to k. But now again this is the sum from k equals to 0 k equals to 0 up to infinity of the probability that n is equal to k times, now this expectation, if n is equal to k, this is the expectation of s of the sum from I equals to 1 up to k of xi, but then by 1, this is equal to the sum from k equals to 0 up to infinity of the probability that n is equal to k times phi x at s at k. Okay? But now, if we actually look at what this is equal to the expectation of phi x s, which is a number, to the random variable n. So this in particular is equal by definition of phi n evaluated at phi x of s. Okay, so using what we are saying, okay, so the corollary is that phi of zeta n of s is equal to phi of zeta n minus 1 evaluated at phi x of s, which implies that this is equal to phi x composed with phi x composed with phi x at s n times. So the theorem, I'll write it in the next page. So the theorem is the probability of extinction eta of the Galton-Watson process with distribution x is the smallest non-negative solution to the equation phi x of s is equal to s. Okay, so you have to look at the fixed points of phi x of s, where phi x is the generating function of x. So the corollary, okay, and so one of the things is, so let's, before the corollary, let's put an observation. The observation is that phi x of 1 is equal to 1 for every x random variable. Okay, so the probability that of extinction is less than 1 if probability of extinction is less than 1 if there exists another solution to phi x of s equal to s in 0, 1. Okay, so then it's just the only thing that you need to check if there exists another solution, because we always know that this one is a solution. So the corollary, by using this observation, the corollary is that if expectation of x is equal to mu, which is bigger than 1, then the probability of extinction is less than 1. And if mu is less or equal than 1, then the probability of extinction is equal to 1, except if the probability that x is equal to 1 is equal to 1. Okay, so if everybody has exactly one offspring, then you have an infinite sequence. But if you don't, if you have exactly one offspring, then this process will never end. But this is exactly the only case in which this happens. Okay, so one of the things is, if you want to check fast if the probability of extinction will be 1, just check the expectation of your random variable and check if this is less than 1 or not. Okay, so I'm not going to cover the central limit theorem for this exam. Okay, so central limit theorem is not part of G2, but will be part of G3. Okay, good luck studying for the exam, and I'll be online soon to answer your questions.